All right, we're going to take a look at the fourth video in our series on isoparametric quadrilateral elements, where we take a look at how the stress results come about. All right, so first we're going to go ahead and review the stiffness matrix equation. There it is. We might remember this from the last 3 videos or so. We have our Jacobian matrix. We have the constitutive matrix, which involves all the material properties based on Hooke's law, being careful to note whether you're using plane stress or plane strain conditions. We have the thickness of the element, and we have our strain displacement matrix, which, as the name implies, of course, relates our strains to our displacements. So for now, please remember these 2 aspects in the upcoming slides: the Hooke's law that we have here and the strain displacement matrix equation. Okay, so now we're going to go ahead and review Gauss quadrature, have our integral equation for the stiffness matrix, and of course Gauss quadrature takes those integrals and replaces them with summations, and since inside the integrand we only have a cubic polynomial at any given location, we only need to use 2 Gauss points in either direction. Okay, so that's the substitution that it makes. There's our element, a 2x2 grid for the Gauss points, and there are all the locations. So all this was covered in the previous video. And of course our weighting factors are just 1. So the important thing to note is that our strain displacement matrix, B, is already known at these Gauss points. And since it's already known at the Gauss points, why not solve for the strains and stresses at those points first? And so that's exactly what it does in FEA software, and the other advantage of that is it turns out those locations happen to usually be the most accurate. All right, so there are the 4 Gauss points that we have inside the element. We're going to take a look at an example for the first Gauss point, examining what the strains would be. So using that first equation that we said to remember, the strains equal to just our strain displacement matrix at Gauss point 1, which we know, multiplied by the displacements for the element. So that gives us the normal stress in the XY directions and the shear stress at Gauss point 1. We go ahead and use Hooke's law, using the strains that are known there in conjunction with our constitutive matrix, to then find our normal stresses and our shear stress at Gauss point 1. Okay, now a question you might ask is, if you've been using something like ANSYS or NX or FEMAP, a lot of times it will report stresses at the nodes. And you might ask, well, how does it do that? And I wish I had a really exciting answer, but it turns out the answer is just extrapolation. It just extrapolates from the results it has at the Gauss points. And so you'll notice I try to put the exclamation point to really make it sound exciting. Don't know if I succeeded with that one. So we have node 3. We're going to use node 3 as an example so we can find our stresses at node 3 by using a summation of individual products of the shape functions multiplied by stresses at the Gauss points. And these shape functions are a special form of shape function known as Gauss shape functions. And really the only difference is it's just the scale. Otherwise, they represent the regular shape functions we had from previously exactly. All right, let's go ahead and take a look at the Gauss shape functions. Just like, as we just mentioned, just like regular shape functions, except the Gauss points are used as the corners instead of the nodes. It just changes the scale. So that's kind of like a little teeny tiny grid. Oh, there we go. Nope. There we go. Okay. Little teeny tiny grid. Okay. There are these natural coordinates that we just put a little prime at the end of to say, hey, these are the Gauss-scale natural coordinates. And so the Gauss points, using those Gauss-scale natural coordinates, those become -1 and 1, where the nodes, those then become plus and minus square root 3. And they become plus minus square root 3 because, well, if we looked at the regular natural coordinates, You know how the nodes were like at +1, -1, things like that, and the Gauss points were at 1 over square root 3? Well, now that we changed the scale, since the Gauss points are at +1 and -1, then these become ± square root 3. Just change the scale. All right, so we're going to go ahead and take a look at an example to demonstrate the extrapolation process. All right, I'm going to go back a couple slides to say that when I say the extrapolation process, we're looking at this portion here, okay? We're going to assume that this portion where we find the strains using the strain displacement matrix and the displacements at each Gauss point, then subsequently finding the stresses from those strains in the constitutive matrix at each Gauss point, we're going to assume that that is relatively straightforward, that you're able to do that okay. And now we're just going to look at how exactly we can use those Gauss shape functions to extrapolate stresses from the Gauss points to the nodes. Specifically, we're going to look at node 3. And we're just going to look at one stress instead of the whole vector. We're just going to pretend that we're looking at the x direction stress. All right, let's go ahead and draw out our element there with our Gauss shape functions. And we'll go ahead and put in some values for our stresses at each of those Gauss points. All right, we got 1,000 at Gauss point 1, 800, 600 at Gauss point 4, and 400 at Gauss point 3. And the first thing we're going to do is we're going to evaluate the Gauss shape functions at square root 3. Why? Because if we go ahead and look at our nodes over here, node 3, the coordinates are square root 3 in our Gauss-scale natural coordinates. So that's what we'll go ahead and do. Oh, I just went through a lot of slides really quickly there. All right. So we're going to go ahead and evaluate those shape functions first. All right. There we go. There's all of our Gauss-scale shape functions. Gauss shape functions, same form as those regular shape functions, right? We just changed the scale. We have xi and eta prime instead. We'll go ahead and make those substitutions there, replacing xi and eta prime with square root 3. We'll go ahead and evaluate each of those values. Great. All right, so now that we have that, we can combine that with the corresponding Gauss point stress values, okay? That's what we had over here. These are the stress values. So we're going to go ahead and combine those. All right, so we can go ahead and say that our stress at node 3 in the x direction is equal to each of these shape functions that we have evaluated over here multiplied by the stresses at each of the Gauss points, and those should be a g right there, and should be x's right here, just the x direction. Go ahead and make those replacements, and we'll make a replacement with those stress values, and we'll solve. There we go. Spent probably too much time coloring that. Solve for that, get 180 psi. Okay, let's just go ahead and see, does that make sense? So, and the question is, does that make sense? We'll go ahead and draw out our values here. These are the original values of the stress in the x direction at each of those Gauss points. We find that that's 180 psi. At node 3, we see that the Gauss point stresses do decrease towards Gauss point 3, and hence even more towards node 3, right? So it's kind of like 1,000 psi decreases to 400 psi, and it further decreases to 180 psi, pardon me. And so we could assume that it would continue to decrease towards node 3. It seems like this value should make sense. So that brings us to the reflection questions. The first reflection question is, where are stresses evaluated at first in an isoparametric element? The next question we have is, why? Why are they evaluated first at those locations? And how are they evaluated at those locations? The next question we have is, how are the nodal stresses determined? And next is, can one element accurately capture stress concentrations? Will neighboring elements predict the same stress at a common node? All right, and so with that should conclude this video on predicting stresses within quadrilateral isoparametric elements. And not only that, it also concludes the 4-part series that we have on linear isoparametric quadrilateral elements.